Hello and welcome. In our lesson today, we are going to discuss two factors that affect the rate of a reaction, and these are pressure and a catalyst. Now let's start with pressure. Now pressure only affects reactions whereby either the reactants or the products are gases. So it does not affect solids or liquids. Now if you were to increase the pressure by compressing the volume, what happens is that you will be bringing the particles of a gas closer to one another. So this of course increases the chances of effective collisions happening, which in turn speeds up the rate of a reaction. So that is that. Now moving on to the next one, the catalyst. Now a catalyst is a substance that speeds up the rate of a reaction but remains chemically unchanged at the end. That means that a catalyst speeds the rate at which a reaction takes place, ensuring that it occurs within a shorter period of time. But at the end of that reaction, the way the catalyst was at the beginning is the way it will be at the end. It has not changed at all. Now, there are several examples of catalysts. We have a common one, manganese 4 oxide. We also have iron. Iron is used in the manufacture of ammonia in the Haber process. So there are actually several catalysts, but the type of catalyst used is specific to a reaction. That means that you cannot use one catalyst for all chemical reactions. No, only for certain ones. Okay, now we know that at this point, a catalyst speeds up the rate of a reaction. How does it do so? A catalyst lowers the activation energy of the reacting particles. Now, in our previous lesson, we discussed activation energy. This is the minimum energy that is required by particles to react with one another in order to form products. So you find that sometimes particles may collide with one another but fail to react because they don't have the necessary activation energy. So this is where a catalyst comes in. So a catalyst lowers the activation energy, ensuring that the reaction can proceed. A catalyst also provides a surface of Now, taking you back to our previous lesson on surface area, we said that if you were to have a larger surface area, the rate of that reaction is also going to be fast. A lower surface area slows down the reaction. Now, if you have catalysts that are in solids, that are in solid form, which most are, you find that if you have it in powdered form, you will be increasing the surface area of the catalyst. So what will happen is that you'll provide a larger area for the particles to react with one another, therefore speeding up the reaction. Now, I want to make that clear. A catalyst will speed up the rate of a reaction, whether in form of lumps or in powdered form, but it's more effective in powdered form because it provides a larger surface area for the particles to react with one another. So let's do an example of a reaction that can be catalyzed by a catalyst. Now this is it. So over here we have hydrogen peroxide. Hydrogen peroxide decomposes to form water and oxygen. Now normally this reaction takes a long time. But if you were to introduce a catalyst, which in this case is manganese 4 oxide, what happens is that it speeds up the rate of the reaction. So you'll end up collecting more oxygen within a shorter period of time. So how do we represent this information using a graph? As such. So over here, we have a comparison of two curves. One for a reaction whereby we are having a catalyst being used. So, sorry for that. And the second one is an uncatalyzed reaction. It does not have a catalyst present. So as you can tell, the reaction catalyzed by a catalyst has a curve that is steeper, showing that oxygen is collected very quickly within a shorter period of time. For the uncatalyzed reaction, collection of oxygen gas is slower. But at the end of it, they both level. So leveling off simply means that the reaction has stopped. So production of oxygen has stopped. Now the amount of oxygen collected at the end for both cases is the same because we are talking about using the same mass or volume of using the same volume of the reactants. Now let us proceed to the next part of our lesson. Let us test our knowledge on our understanding of the concept of pressure and catalyst by basing this on KCSE questions. Okay, so our first question is from 2021, paper 2, part A. Chemical reactions occur as a result of the collision of particles. Give a reason why not all collisions are effective. Now, the reason is because some don't have the necessary activation energy and therefore the reaction cannot proceed. Part B, state and explain how the following factors affect the rate of reaction. Roman 1, surface area of the reactants. So an increase in surface area increases the rate of a reaction. Why? Because it increases the area of contact of the reacting particles. This in turn increases the effective collisions. Roman 2, pressure. Now, pressure only affects reactions that involve gases, not liquids or solids. This is because gases, unlike liquids and solids, can be compressed, therefore altering their pressure. Now, in gases, an increase in pressure increases the rate of a reaction. This is because it brings particles close together, which in turn increases effective collisions. And that is our first question. Our next question. The curves below were obtained when two equal volumes of hydrogen peroxide of the same concentration were allowed to decompose separately. In one case, manganese 4 oxide was added to the hydrogen peroxide. Which curve represents the decomposition of hydrogen peroxide with manganese 4 oxide? Explain. So the first thing we should ask ourselves is, what is the role of manganese 4 oxide in this reaction? Now, manganese 4 oxide acts as a catalyst for the reaction. So normally hydrogen peroxide takes a long time to decompose without a catalyst. So with the introduction of manganese 4 oxide, the reaction occurs very fast. So we can clearly see that we have curve 1, which is steeper than curve 2. That means that with curve 1, a catalyst was used, and therefore the volume of the gas produced was collected within a shorter period of time. So the answer is curve 1, because manganese 4 oxide acts as a catalyst, speeding up the rate of decomposition of hydrogen peroxide. Our next question. The diagram below is a sketch of the graph of a non-catalyzed decomposition of hydrogen peroxide. On the same axis, sketch the graph for the decomposition of hydrogen peroxide when manganese 4 oxide is added. Now, manganese 4 oxide again acts as a catalyst for the reaction. But in the reaction that we have, in this reaction, we are being told that it's a non-catalyzed decomposition of hydrogen peroxide. Simply put, decomposition of hydrogen peroxide takes place without a catalyst. A catalyst speeds up the rate of a reaction by lowering the activation energy of a reaction. So if we were to use manganese 4 oxide, what will happen is that it's going to lower the activation energy, therefore speeding up the rate of the reaction. So this will give us a curve that looks like this. And there we have it. So this brings us to the end of our lesson. I hope it's not only been educative but fun as well. See you next time.